Hello, am I audible? Okay, so I will just wait for 5 minutes more if other participants also join, and then I will start. Okay, so 6:05 p.m. now. So I was waiting if a few more participants would be joining, then it's okay. So let me start. So first of all, hello everyone. Uh, Good evening, and I am Sayoni Sinha. So as you know, I will be taking it will be kind of tutorial session or some problem solving session. So if you are following the NPTEL lectures that are getting posted every week, and if you have any doubt from that, so you may ask those to me or other session conductors. So that is the purpose of this live session. And also, I will be trying to discuss some problems with you so that it is better, you get better understanding of the topic. So our course is, as you know, foundation of cryptography, and today I will be discussing about things that were posted as week 1 and week 2 contents. Okay, so week 3 contents, as I saw, it just got posted yesterday probably, so we will discuss about that next week. And for today, week 1, which was mainly introductory thing, and week 2 material, I'll be discussing some problems from that part. If you have any question before I start my problems and their solution, if you have any question, you may unmute yourself and ask if you have any doubt. Okay, great. So I assume you have nothing to ask as of now. Is there? Okay. So, okay, don't write in chat, as there are very few participants in the meeting. You can just unmute yourself and ask if you have anything. So I will just share my screen. Okay. So my screen is visible, right? Is my screen visible?
Yes, ma'am.
Okay. Okay. Thank you. Okay. So let me proceed. So broadly, the topics that I will cover in today's this session is historical ciphers and cryptanalysis. Then comes the concept of perfect secrecy, and then we will discuss about what are the modern cryptography concept, as you have already learned from the video. So we will discuss some problems on that, and then comes one very important topic of pseudo random generator or PRG. So the first problem, so basically for every problem I will share my screen. You can see the problem, and I will give you a few minutes to read the problem and think about it and get back to me if you have the idea of how to solve this, the answer. Then I will discuss the answer for all also. So let us first read the problem. So it says that consider an instance of shift cipher with the probability distribution over the message space as follows. So probability of message being A is 0.4, probability of message being B is 0.3, and probability of message being C is 0.3 again. So what is the probability that the cipher text is D? So that's the problem, and there are few options given. So think about it a bit. So what is the plain text space here? I would like the session to be more interactive, so that will be better. So can anyone tell me, so what is the exact plain text space or message space here? Anyone want to try what will be the message space? So already you can see here, right? Probability of message being A, being B, and being C are given. So clearly A, B, C, these three are element of the message space or plain text space, right? So okay, let me just recap once. So for any crypto system, I assume you all may be the like very beginner. If you are not still, it is fine. Then like for any crypto system, you have one plain text space, and when you encrypt that plain text, you need some key, which is essentially a secret information. And using the key and the plain text, your encryption algorithm runs and you get back some ciphertext, right? So that is the very basic concept of cryptography. And the encryption key that is secret, if we talk about symmetric cryptography, and if we talk about, say, public key cryptography, then there are like concept of two keys, public and private. Then with the encryption key is basically public, with that anyone can encrypt a message for some targeted audience, and that particular receiver is able to decrypt the message using the private or secret information, which is the decryption key. So uh, focusing on this particular problem, you can see here that A, B, C, these are of course essentially element of plain text space as it is given already in the problem. And there is nothing, no specification about the key space, and also there is no specification about the ciphertext space as you see here in the problem. No explicit specification. But if you are aware of shift cipher, what it does basically. So in a shift cipher, you have one key, right? That key is essentially some alphabet between A to Z. So if we denote letter A with the value 0, letter B with the value say 1, and so on. So letter Z with the value 25. So we have 26 letters in the alphabet, right? So the key can be anything between anything among them, 0 to 25, representing each character of the English alphabet. Then this, what the shift cipher does is that with every plain text, it will just shift its position by that key amount. So let's say if the key is B, which means the value is 1, then if you have plain text message A, the ciphertext will be one space shifted. So A will be shifted one space and we get B as the ciphertext. If you are given, say, E as the plain text and key is B or 1, then E will get shifted by one space and we get F as ciphertext. So if I am clear with that, so let us proceed here. They're telling A, B, C are the message space or plain text space element, and what are the probability of occurrence of each one of them. So if you sum up all these three, 0.4, 0.3, and 0.3, we get 1, right? So that is the probability of the whole message space. Like if you have some elements in this message space, sum of the occurrence of probability of each one of them must be 1. So it is clear from this instance of problem that there are no other plain text element in the plain text space. Only A, B, C are the only 3 elements present in the message space. Now, what is the probability that we get ciphertext D? So how we can get ciphertext D? So anyone like to comment on the answer? I will just ask once again. Okay. So let's see the solution. Basically, if the ciphertext is D, that means one event can be that plain text was A and the key was D, whose value is 3. If we start A with 0 value, then D has value 3. So A will get shifted by position 3 and we get D as ciphertext, right? A after that B, C, D. So A gets shifted by 3 places. So that is one occurrence by which like we can get ciphertext as D. Also, what can be the case? It can be the case that plaintext was B and the key was C, whose value is 2. So B gets shifted by 2 places and the ciphertext is D. And another event, probable event is that the message was C and it gets shifted by just 1 space and it becomes D, the ciphertext. Right, so these are the only possible cases. There are no other messages in the plaintext space. So these are the only 3 probable events that may occur. And what we get is that, so you can say that as we are given, probability that message is A is 0.4 and all the key occurrence essentially, so in shift cipher, any key from the alphabet can occur with exactly same probability. We have 26 letters in the alphabet, so probability that any one of them is uniformly randomly chosen from that key space is the probability is 1 by 26, as there are 26 elements. So I have taken all these probability of k equal to D or probability of k equal to C or probability of k equal to B. All of them are 1 by 26. So I have extracted the value and inside it was just 0.4, 0.3 and 0.3, which is nothing but 1. So we get the result as 1 by 26. So this is the probability that we wanted to calculate it, the probability of occurrence of D as the ciphertext. Okay. If anyone has any doubt, you may ask. So let me proceed to the next problem. So this is very similar. I hope if you have understood the previous problem and its solution, of course. So you can try these ones to solve yourself. So let's read the problem first. Consider an instance of shift cipher with the probability distribution over the message space as follows. So again, we are given some probability value of the possible message text space, right? So probability of message equal to A, message by message, I mean plain text, right? So probability that plain text was A is 0.3, probability that plain text is B is 0.6, probability that plain text is C is 0.1. Then identify the correct statement from the following. So the options given are probability that the ciphertext is D is the same as the probability that the ciphertext is E. Next option, probability that the ciphertext is D is less than the probability that the ciphertext is E. And then probability that the ciphertext is D is more than the probability that the ciphertext is E. And the last option is nothing can be said regarding the probability that the ciphertext is D and the probability that the ciphertext is E. So if you remember the previous example, just the before example we discussed. So anyone want to comment about that? So is it at all possible that nothing can be said regarding the probability that the ciphertext is D? We are again talking about shift cipher. We are again given some plain text distribution probability. Anyone want to say anything about that? The last option is possible or not? Okay. So as we saw in the last example, so we already calculated for the similar problem the probability what is the probability of the fact that ciphertext comes out as D. So that answer was 1 by 26, provided that the only possible plain text were A, B, C in that case. Why? Because the sum of those probability was 1. So here also, if you observe, only A, B, C are the 3 possible plain text here, because 0.3, 0.6 and 0.1 again sum up to 1. So no other plain text are there in this particular instance of problem. And for shift cipher, again, key can be any one from the all possible 26 keys. So here also we can say that obviously probability that the ciphertext is D is similarly can be calculated as 1 by 26. And same can be the probability that the ciphertext is E, because for E, what we will do? We will just, if you say the previous example, we'll just see that what is the probability that message was A and probability that key was E in this case, because we want E back as ciphertext. So value of E will be 1, value of E will be 4. So A will be shifted by 4 places and we will get ciphertext as E. And similarly, what will be the probability that message is B and key is D? And what is the probability that message is C and key is C, right? So like that, we will again get back 1 by 26 as the probability of the ciphertext being E. So clearly the first one is our answer. The probability that the ciphertext is D is the same as the probability that the ciphertext is C. Am I clear? Okay, let me proceed to the next problem. So here is a problem on perfect secrecy. So if you recall from the lectures, what is the concept of perfect secrecy? So there is, in every crypto system, when proving its security, we always consider existence of some random adversary who has some specific power. So for the case of perfect secrecy, we assume unbounded computation power of the adversary. So who is adversary? Adversary is someone who is always trying to attack our crypto system and make it fail. We want to keep our crypto system secure against an adversary. And in case of perfect secrecy, we assume that adversary has unbounded computation power. So it can try to attack the crypto system using any way possible and taking any amount of time it can have, which is not, of course, real or practical thing, but we assume this for perfect secrecy. So unbounded adversary, and we still say that the adversary, if it has access to see the to observe the ciphertext of any plain text, so it is like ciphertext only attack, right? So it get to observe only the ciphertext, and seeing the ciphertext, it should learn nothing about the underlying plain text, right? So in case of perfect secrecy, so let's focus on this particular problem. Which of the following conditions is or are sufficient to get a perfectly secure encryption scheme? Options are: ensure that key generation algorithm outputs a uniformly random key from the key space, ensure that encryption algorithm is randomized, ensure that the key is as large as the plain text, and then none of these. Anyone wants to contribute about the solution? Okay. So proceeding to the solution, basically key generation algorithm should output, of course, a uniformly random key from the key space. That is a requirement for the scheme being perfectly secret, but that is not a sufficient condition for the scheme being perfectly secret, right? Okay, someone answered this. So I would request, because there are very few participants, if you are answering, please unmute yourself and say, that will be better for me, right? Okay. Thank you. So yes, so the first option is necessary, but it's not sufficient for ensuring perfect secrecy. The second option is not even necessary for the scheme being perfectly secret. So this thing, the necessity that encryption algorithm should be randomized will come into scenario when we assume some more powerful adversary. Okay. So that's not in our context right now. And the third option, that key is as large as the plain text, or so of course key should be as large as the plain text to ensure perfect secrecy, but that's not sufficient. Okay, so our answer is none of the above. So we'll proceed to the next problem. So this is very straightforward question from book or from lecture, whatever you say. Which of the following are valid conditions for perfectly secure encryption scheme? Anyone would like to answer? There are few options given. Probability that this capital M is any random variable to take value from plain text space, and small m is a particular value. So by writing probability that m equal to small m, we mean that the probability that the plain text is selected as the specific message m from the plain text space, right? So probability that capital M equal to m provided ciphertext is small c is equal to probability of capital M being small m. So anyone wants to answer this question? You can see the screen and just try. This is the very basic condition that we iterated for part secrecy.
First one.
Right, first one. Who is it? Siddhartha?
No, it's me, Renji.
Okay. Okay, thank you. So this is the first option, right? It is very straightforward. So what do you mean by that? I will just recap once. So probability of capital M equal to M, when we just see this thing, we say it's the prior probability, right? So when you have not seen, when the adversary has not seen the ciphertext, what it knows is that the plain text distribution, right? So from the plain text space, what is the probability that every plain text can be chosen while encrypting? So that probability distribution is known to the adversary, and it knows the encryption algorithm, and then it get to see the ciphertext. And even after seeing the ciphertext, it sees the ciphertext as, say, small c, but upon seeing that, still what it can guess about the underlying plain text of that particular ciphertext is just the same, has just the same probability distribution as it would have known beforehand about the message space distribution. So this is called the right hand side is the prior probability, and the left hand side is posterior probability. So these two has to be necessarily same to ensure perfect secrecy. Okay. So proceeding to the next problem. So here is some problem that you can actually have to compute on pen and paper, or you can think also. So there is no option provided. So let us first read out the problem. Let us assume a symmetric key encryption scheme. As I said earlier, symmetric key encryption scheme means that there is only one key which has to be secret, and that key is known only to the sender of a message and receiver of a message. Only these two parties are aware of the secret key, and that's why this is symmetric key encryption. The key on both sides of the sender and receiver are same, so symmetric key. So let us assume a symmetric key encryption scheme with message space capital M equal to 0 to 13. All the numbers 0, 1, 2, 3 to 13. All these are probable messages. And key space is 0 to 14. Key generation algorithm chooses a uniform key from the key space. Encryption and decryption are defined as follows. So how do you encrypt and decrypt here is that while encrypting the plain text small m with key small k, what we do is that we do m plus k mod 14. So modular arithmetic is going on here. So we just add the plain text with the key and then apply modulo 14. And decryption is C, which is the ciphertext. So C minus the key K modulo 14. So these are the encryption and decryption operation defined. So what do you think about the perfect secrecy of this scheme? So if you want to take 2 minutes to think, so you are welcome to think. I will just pause for 2 minutes.
I think
Hint
it
is that,
perfectly
yes.
secure.
Sorry?
I think it is not perfectly secure.
Why is that?
Because the key space only containing 15 characters. So by brute force attack itself, we can find the key, right?
Your
We
intuition
can
is
check one by
correct,
one.
of course. But if you were asked to show this by calculation, so just show that somewhere the required condition of perfect secrecy, that we say that prior probability of occurring some message and the posterior probability of occurring some message after seeing the ciphertext. So that does not match somewhere, right? So, yes, it is not perfectly secure. Thank you. And I'm sorry, one announcement. Just it is. This Zoom meeting link is there, so it is showing that it will so they, in the free Zoom account, they just allow 40 minutes meeting, I guess. So this meeting will continue. You please, if this meeting ends, you please join in the same link again. Okay, I'll just have to make this announcement. So I will just proceed to the solution as someone mentioned, right? So uh, here, basically, each message, if we say that they can occur with same probability, which is 1 by 14, but then probability that m equal to 0 upon c equal to 0. So when we say that the ciphertext is 0, what is the probability that the plain text was 0? That can occur actually in two cases. Either if k is 0, then also 0 plus 0. So what we do is that m plus k mod 14, right? So 0 plus 0 mod 14 is 14, and also 14 plus 0 mod 14 is also gives 0 as ciphertext. So there are two cases where this can happen. So this probability is 2 by 15. So, but if you see the other cases, it will for c equal to 0 and the probability that m was 1, that is only 1 by 15, and that essentially does not match with this probability of 1 by 14. So we can conclude that this condition of perfect secrecy does not hold. So this has to be held true for all of m and c possible from plain text and ciphertext, right? So that's how we show mathematically that this scheme is not perfectly secret. Okay. So I will proceed to the next problem. Let us recall encryption with one-time pad. So what happens in one-time pad is that you have some plain text message, and the key is you do not reuse same key, right? So every time the operation is very simple. Encryption operation is just bitwise XOR of the plain text and the key, but the key is never reused, and the length of the key is always has to be exactly same as the message length or plain text length. So that is one-time pad, and one-time pad is an example of perfectly secure scheme. So in this problem, we are talking about that, let's say in a one-time pad scheme. So this is an observation that if the key is just L length string of all zeros, then what we get as ciphertext is that as we XOR it with the message string, all 0 is XORed with any string gives back the same string, right? So m XOR k will give us back the m itself. So the ciphertext is nothing but the plain text in clear, right? So one considers to modify the one-time pad by only encrypting with k not equal to 0 to the power l. So 0 to the power l is l bit string of all zeros. So as we said that the length is specified as l. So the key length is l. The message length also must be l, and message is some binary string of length l. And because the key being all 0 makes the ciphertext exactly same as the plain text, we want to avoid this scenario, and we say that we will make the scheme little bit modified and say that we will exclude this all 0 string from the key space basically. So is this modified scheme will still be perfectly secret? Anyone would like to answer? just think upon this. So basically, one key we are always not allowing to be chosen. Just few example earlier we said in multiple choice question that choosing uniformly random string from the key space is a requirement for having perfectly secure scheme. So if you can relate with that and say something. No? Okay. So the answer is that, of course, this scheme is not going to be perfectly secret. Why? Clearly, if we exclude the key, this particular string 0 to the power L from the key space, which is the L length binary string, the key space size becomes 2 to the power L minus 1. So what are the total possible keys if we allow just L bit binary string as our key? So that length is that number is 2 to the power L. So among 2 to the power possible keys, we are excluding this 0 to the power L scenario. So we get the key space length as 2 to the power L minus 1, which is of course less than 2 to the power L. And our message space still remains the same. So the message space length is 2 to the power N. So here becomes the scenario that key space is less than message space, which is not allowed, which is not uh, allowed for having a perfectly secure encryption scheme. So that's why we say that this crypto system is not perfectly secure. Okay. Here, once again, another mathematical problem to prove a system's perfect secrecy. So we are already saying that this crypto system is perfectly secure, but you have to mathematically prove that. So you are given plain text space as P, which is A comma B. There are only two possible plain text. And key space size is 5, where K1, K2, K3, K4, and K5 are the possible keys. Ciphertext can be anyone among 1, 2, 3, 4, 5. And how the encryption is done, that is presented as in a matrix form here. So this matrix means that plain text A upon applying key K1 gives ciphertext 1, and plain text B upon applying key K1, the encryption algorithm gives back ciphertext 2. And like that, everything is given in the matrix. And also it is given that if you choose two positive real numbers alpha and beta such that alpha plus beta is 1, and define that probability of choosing K1 as the key from key space, choosing K2 as the key from the key space, and also choosing K3, all these probability are given as alpha by 3, and probability of occurring K4 and probability of occurring K5 both are given as beta by 2. So as you see here, basically all of these will sum up to 1 only, right? So these three are alpha by 3, summing up to alpha totally, and this summing up to beta, and alpha plus beta is already given as 1. So as expected. Now prove that the crypto system achieves perfect secrecy. So how do we, what is the approach basically that we take to prove that a system is perfectly secure? Essentially, we prove that same thing, right? That probability of occurring a message M equal to some particular message small m, which can be A or B here. So probability that selected message is A should be equal to probability that after seeing some cipher text small c, I'll just do it just 2 minutes to join. Okay, I will resume. So we were discussing about how to mathematically prove that this crypto system is perfectly secure. So basically, the approach will be, of course, that probability of capital M equal to small m, that is occurrence of any particular message M, and that should be equal to probability that capital M equal to small m, provided capital C is equal to small c. That is for any specific ciphertext. Informally, if we say that seeing any ciphertext, the adversary should not uh, guess what can be the underlying message of that ciphertext apart from the previous information that it already had about the plain text distribution. So after seeing the ciphertext also, it should have no extra information about the distribution of plain text of that ciphertext. Okay. So let us see the mathematics here. So we have the two messages A and B as the element of message space. So probability of capital M equal to A is equal to probability of capital M equal to B, which is half. Okay. Now, if we calculate what is the probability of ciphertext being 1. So there are two messages, probability that there are two messages A and B. So first case can be the message is A, and then provided message A, what is the probability of ciphertext being 1. And then we say probability that message is B, and what is the probability that ciphertext is 1 provided message was B. So if we see all these probabilities, so this is already half we have seen, and probability that ciphertext is 1 provided message is A, that is nothing but, see the table, that probability that message was A and the ciphertext is 1 only occurs when the key is K1. And what is the probability of occurring the key K1? That is alpha by 3. So that's why we write here half into alpha by 3. And the next expression is also similarly probability that message is B is half, and probability that message is B and the ciphertext becomes 1. That also happens when the key is K3. So which is alpha by 3. The probability is alpha by 3. So we sum up these two and we get alpha by 3. So that is the probability of ciphertext being 1. Similarly, we calculate what is the probability of ciphertext being 2. So that is, if the message is A, then ciphertext is 2 only in this case, when K2 is 2, and that probability is alpha by 3. And when the plain text message is B, the ciphertext is 2, that occurs only when the key is K1, and that probability is again alpha by 3. So replacing those value, we again get alpha by 3 here. Similarly, exactly same way, we calculate what is the probability of ciphertext equal to 3. And then the probability of ciphertext being 4. So see in the table that when the ciphertext can be 4. So one case is message is A, which is of probability half, and ciphertext becomes 4 only when key is K4. And if the plain text was B, then ciphertext is 4 only when the key is K5. And both these occurrence of probability, occurrence of key as key 4, that probability, and occurrence that the key is K5, that probability both are beta by 2. So you replace in this expression. So, and summing up them gives us back beta by 2. And probability that ciphertext is 5, that also have the exactly same probability. And now if we calculate, we need to now calculate the posterior probability, right? So, provided that ciphertext is 1, what is the probability that the underlying message of this ciphertext was A? So this thing, using Bayes theorem, you can just calculate probability of messages A into probability that provided message is A, ciphertext is 1, divided by probability that ciphertext is 1. So this is nothing but the Bayes probability theorem. If you remember, that probability of A by B into probability of B is equal to probability of A into probability of B upon A, right? So using that theorem only we calculate, and replacing the value from this previously computed value, we get back half. And as you see, probability of message equal to A upon ciphertext is 1 is half, which is just equal to the prior probability, means probability of message being A. Okay. And in the exact same way, you can calculate for all the values that probability of M equal to A upon probability of C being 2, that will also give you back half. Like that, every possible combination of message and ciphertext, you calculate this posterior probability and you will get back half, which is nothing but the same as prior probability. So that's how we conclude that this given instance of crypto system is indeed perfectly secure. Okay. So if you have any question, you may ask. Okay. So proceeding to the next problem. So this is again a multiple choice question. You can try. So which of the following are correct? All of key generation, encryption, and decryption algorithm are kept secret in the crypto system. All of keygen encryption and decryption algorithm are made public in a crypto system. Both encryption and decryption key are public in a public key crypto system, or only encryption key is private in a private key crypto system. So this is very, I guess, easy question. Anyone would like to answer? I am audible and the screen is shared, right? Someone can confirm? My screen is visible, right? Okay, someone answer in chat. Okay, good. So anyone would like to answer this question? No? So this basically any crypto system having mainly 3 algorithms: key generation, encryption, and decryption. All of these algorithms are of course public, right? So the algorithms are not secret. Okay. So algorithms are not secret. What is secret is the secret key of the crypto system. And what is secret key? In case of private key crypto system or symmetric key crypto system, there are only one key which is shared by the sender and receiver, and only they are aware of the key. So that thing has to be secret. So in a private key crypto system, the encryption key is secret. And in a public key crypto system, another option is that both encryption and decryption key are public in a public key crypto system, which is of course not true. In a public key crypto system, basically the encryption key is public, using which anyone can encrypt a message to a targeted receiver. But that targeted receiver should only be able to decrypt the message and using his or her secret decryption key. So encryption key is public, but decryption key is private in a public key crypto system. Public key crypto system is also said to be asymmetric crypto system. Okay. So okay. all the algorithms are public, and in a private key crypto system, encryption key is private. These two are the correct statements. So next problem. Let's read out it. Let us consider an encryption scheme designed to encrypt L+1 bit messages. A L+1 bit key K is generated by first choosing a uniform random L bit string and then taking the last L+1th bit as the XOR of previous L bits. Encryption and decryption are performed in similar manner as of one-time pad. So is this scheme perfectly indistinguishable to an adversary? What do we mean by this indistinguishability thing is that, let's say the adversary provides to some verifier the two messages, say M0 and M1 of its choice. So adversary sends M0 and M1 of its choice to a verifier. The verifier will encrypt any one of them according to its wish. Let's say it just tosses a coin, gets back head or tail. Depending on that, it chooses a bit 0 or 1. And if it gets 0 as a result of toss, so it will encrypt M0, otherwise it will encrypt M1. So it will encrypt M0 or M1 and send back to the adversary. The adversary, seeing the ciphertext, should not be able to distinguish that whether it was an encryption of M0 or encryption of M1. So now this is what we mean by the indistinguishability to an adversary. Now you are given a crypto system where we are saying that the encryption operation is nothing but as you do that, XORing the message with the key, right? But the key is not a uniform random choice from L+1 bit strings, right? So among all possible L+1 length bit strings, you are not uniformly randomly choosing one. You are choosing L bit random string, and then the L+1th bit, last bit, is the XOR of the previous bits. So is this still remain indistinguishable to an adversary? Anyone has any input? Okay. So here goes the answer. So if we want to prove a system is not indistinguishable to the adversary crypto system, so we want to prove that the adversary is able to distinguish between seeing a ciphertext between the underlying possible plain text, then what we do is that we give a counter example. So we provide a counter example here. So let's say adversary provides two messages. The two messages can be of its choice only. So the adversary provides two messages as M0 equal to 0 to the power L+1, which means a string of all zeros of length L+1. And the second message M1 is 0 to the power L concatenated with 1, 1. So basically, M1 is a L+1 length bit string where first L bits are all 0 and the last bit is 1. So like that, it chooses two messages, M0 and M1, and then provides it to a verifier. What verifier does is that it outputs encryption of either M0 or M1. And by definition, we are providing that the key is of the form K1, K2, K3 to KL. So first L bits are uniformly random. And the KL+1, this bit is nothing but XOR of K1 to KL. So when M0 gets encrypted with K, what we get is that the C0, if we denote that C0 is the encryption of M0 with key K, so we get back the key K itself. Why? Because the message string was all 0 and you XOR anything with 0, you get back whatever is the original key here. So this is the key. With that you XOR all 0 bits of the messages and you get back the key itself as ciphertext 0. And what will happen if you encrypt M1 with such a key? So M1 is all zeros till length L and the last bit is 1. So XORing with 1 will flip the bit, right? So C1 is K1 to KL are as it is, and last bit what we denote is as K dash L plus 1 is the inverse of K1 XOR K2 till XOR KL. So XOR of all these previous L bits and you take just the negation of that, and that is the last bit K dash L plus 1. So clearly these two scenarios, seeing the ciphertext, it can easily determine whether the ciphertext is an encryption of M0 or encryption of M1. How the adversary just checks that whether the last bit of the challenge ciphertext, so whatever it gets back from the verifier, we call it challenge ciphertext. And seeing challenge ciphertext, the adversary's task is to say whether the challenge ciphertext is an encryption of M0 or encryption of M1. And here the adversary will just check that last bit of the challenge ciphertext is XOR of previous L bits or not. If it is XOR of previous L bits, then obviously it is an encryption of M0. And otherwise it is an encryption of M1. And with probability 1, literally it can distinguish between these two scenarios. So of course, this crypto system is not indistinguishable 20%. It's not secure. Okay. So you were taught about the concept of negligible function in the lectures, right? So here comes a problem on negligible function. So let's say Pn is a positive polynomial and delta n is a negligible function given. Now you have to prove that Pn multiplied with delta n is a negligible function. So this is already provided as theory, but you have to prove it formally. So, okay, we will take a look at the solution. Delta n is a negligible function as given. And by definition of negligible function, what do we mean by that is that for every positive polynomial fn, there exists an n naught, which is a natural number, so that for all n greater than n naught, for any positive integer n greater than n naught, we get delta n is less than 1 by fn. So inverse of any positive polynomial. So if delta n is negligible, then it should be less than inverse of any positive polynomial. So that is the criteria of being negligible function. Now you have to prove that Pn, where Pn is a positive polynomial, Pn into delta n is also negligible. So what we do is that this condition delta n less than 1 by fn, we just multiply both sides. So Pn into delta n, as it is positive, so you this inequality sign remains same. So Pn into delta n is less than Pn by fn. And you can write this quantity as 1 by f dash n, where f dash n is just fn by Pn. You just bring this Pn below fn and you get f dash n, another polynomial. So with that we can say that so there will be an n dash, so that for all positive integer n greater than n dash, Pn into delta n will be less than 1 by f dash n. So n dash need not necessarily be equal to n0, so that constant term may change, but any positive, so for any positive polynomial f dash n, you will find some n dash such that for all positive integer greater than n dash, you will this condition will be satisfied, that Pn into delta n is less than 1 by f dash n. So that's how we can say that any negligible function multiplied with a positive polynomial gives another negligible function. So this criteria will be used in proving some crypto system security later on. Okay. Another MCQ question. Anyone would like to answer? Identify the incorrect statements from the following. First option, a scheme is COA secure. That is ciphertext only attack. Secure against ciphertext only attack if and only if it is secure against known plaintext attack, KPA. Another option is scheme is KPA secure if and only if it is CPA secure. And then a scheme is CPA secure if and only if it is CCA secure, ciphertext, chosen ciphertext. CPA is chosen plaintext attack, CCA is chosen ciphertext attack. So there are 4 kinds of attack that have been included in this question. Ciphertext only attack, known plaintext attack, chosen plaintext attack, and chosen ciphertext attack. Anyone would like to answer this question? Okay, so let's once recapitulate that what do we mean by ciphertext only attack. So these are nothing but various power of adversary that we assume while designing a crypto system. So the adversary power can vary. Ciphertext only attack, in that case the adversary gets to see only ciphertext. So it just eavesdrops on the communication channel. There is one sender and one receiver. Sender is sending some encrypted message through a public channel to the receiver, and the adversary acts just as an eavesdropper to the public channel and gets to see the ciphertext that is being communicated. That's it. It does not have any extra information apart from that. So that is what ciphertext only attack. And using that, it just wants to attack the crypto system. And what does it mean by attack on the crypto system? That is also needs to be defined. For now, we assume that the gaining extra information about the underlying message of the ciphertext apart from the already known distribution of message space. So apart from that, the adversary should not know anything. That is how we say that the crypto system is secure. So that is what ciphertext only attack means. And then comes known plaintext attack. Here we assume that the adversary is able to see pair of plaintext and ciphertext message. So it not only just see some ciphertext being communicated, it somehow has the information of the underlying plaintext also for a few couple of communications. So it already has, you can think of a table where it has access to a table where there are a few number of plaintext and ciphertext pair, and with that knowledge, if it is given some unknown ciphertext that it has not seen previously, seeing that ciphertext, whether it is able to gain some extra information about the underlying message or not. That is what KPA security means of a crypto system. And what is CPA security? So that is chosen plaintext attack. So previously in KPA, we said that known plaintext attack. So adversary just gets to know the plaintext ciphertext pair. But in CPA case, it can choose the message for which it wants to see the corresponding ciphertext. So that's how it is chosen plaintext. It can choose the plaintext and it can make some honest party encrypt that chosen plaintext, and it can then see the corresponding ciphertext. So that's how the adversary's power are gradually increasing, right? And then the highest power that we think of an adversary has is CCA secure, where it is chosen ciphertext attack. So where it already has this encryption oracle access. By encryption oracle, we means that the adversary gives any message of its choice and gets back the ciphertext, which is the case of CPS security case. And in CCA security, we say that not only the adversary can get to see ciphertext of its chosen plain text, it can also see plain text of its chosen ciphertext. So it also has access to some decryption oracle where it can query with some random ciphertext and see what plain text it decrypts to. So that's how it has access to some decryption oracle. So basically, in every cases, step by step, from ciphertext and only attack to known plain text attack, then chosen plain text attack, and then chosen ciphertext attack. In each of the cases, the adversary's power is gradually increasing. So if we see this particular question, it says that scheme is COA secure if and only if it is KPI secure. It may be the case that if the system is KPI secure, the concept of ciphertext only security is already satisfied, but it's not the case, vice versa, of course. So the if and only if statement is completely wrong for all these three cases because the ciphertext, because the adversary's power is completely different in each of the cases. So you cannot ensure a higher level of security by just making your system lower level secure, right? So you make your system CPA secure, that cannot never imply that your system is CCA secure as well, where the adversary has more power, right? So the answer is all the above three statements given, all are incorrect. Right? Okay. Now we proceed to the next question. So here comes some problems on PRG, that is pseudo-random generator. If we recollect for a moment what is a pseudo-random generator or PRG, so it is basically the PRG is provided as input some seed of some particular input length, and its task is to output some larger length bit string, right? So basically, generating random number is a necessary task in various crypto system or various applications, but truly random generation is a really difficult task, right? So it is not at all efficient. So we proceed for pseudo random generation. So seeing at like looking at the output of pseudo random generator, you should not be able to distinguish the output from a uniformly random generated string, right? So that is the whole purpose of PRG. Also, you should be able to expand the input. So the input seed is always of lesser length and the output of PRG is always of longer length. That is the property of PRG, that expansion needs to be there in PRG algorithm. So by recapitulating this concept of PRG, so let's see this particular question. So let G be a secure PRG. Also, what do we mean by security of a PRG? We said expansion is necessary, that's okay. But another important property of PRG is pseudo-randomness. That is the whole purpose of building this concept of PRG. So as I said that the security of PRG necessary means that pseudo-randomness of its output string. Whatever the PRG output, that bit string should be indistinguishable from uniformly random choice of same length bit string. Okay. So true, you should not be able to determine the pseudo-random output with a truly random string. Okay. So let G be a secure PRG, then which of the following is not a secure PRG? You have been provided with 4 different kind of instantiation of PRG and you have to say whether they are secure or not. So whether their output is actually pseudo-random or not. First, okay, I'm sorry, the meeting is again about to expire in 10 minutes, but please join in the same link, okay? So, okay. First option is G1 is GS concatenated with S. S is the seed. So we propose an instantiation of PRG, which is that we already have a secure PRG G. So what we do is that we concatenate the seed S with the output of our provided original PRG GS. So we will see actually one by one all these provided proposed instantiation, whether they are secure or not. So let's first proceed to the first option. So this is a handwritten thing. So just to follow better. So G is already provided, which is a secure PRG, right? G1 is defined as GS concatenated with S. So just assume that the seed S is small l bit long, and the output of the original PRG G is capital L bit long, with, of course, capital L is greater than small l, because expansion is required, as I said. Then G1 is capital L plus small l bit long. Of course, because we are concatenating the seed with the output of the original PRG. So it is capital L plus small l bit long. Now, we say that actually this proposed PRG is not pseudo-random. So how do we prove that? We think of a game between a verifier and an adversary. What verifier does is that it tosses a coin, chooses a bit randomly 0 or 1, and also chooses a seed from small l length binary string. Now, if B is 0, the chosen bit is 0, then it will compute Y as GS concatenated with S. That is our proposed PRG. Otherwise, it just takes a uniform random string from all possible capital L plus small l length binary string. Okay. So this is how you the verifier computes Y and gives it to adversary. What the adversary wants to do is that its task is somehow to distinguish this Y. Like seeing this Y, it has to tell whether it saw an instance of this PRG output or an instance of uniformly random string from L plus L bit binary string. So it has, that's how it distinguishes, right? So it will output a bit B dash, indicating whether B was 0 or B was 1. If B, yes, yes, yes. Hello? Anyone has to say anything? Hello? Okay. I think that's a noise. Okay. So if B dash is B, then the adversary basically wins the game, right? So we will show here that the adversary is successfully able to distinguish between the two cases. How? So after seeing this Y, that it does not know how it was generated by the first method or by the second method, it will just parse Y in Y1 or Y1, Y2. So it will divide it in two parts so that Y2 is small l bit long. So this Y is, of course, capital L plus L bit long, as we said, and it will divide Y1 and Y2 so that the first part Y1 is capital L bit long and second part Y2 is small l bit long. Okay. And then it checks if Y1 is equal to G of Y2. So as you see, the form is such that the first capital L bits is nothing but the original PRG output of the last small l bit. So the adversary will just check, because the PRG algorithm is a public algorithm, right? So it will just check if Y1 is equal to G of Y2. If it is, then return B dash equal to 0. Else return B dash equal to 1. And if it is able to successfully guess the bit B dash, then it wins, and we say that it is not a secure PRG. So how do we say that? So probability that adversary returns B dash equal to 0 provided the actual bit B was 0. So we will just try to see that if the bit B was actually 0 and adversary returned correctly B dash equal to 0. What is the probability? The probability is essentially 1, because always whenever B is 0, this form will always satisfy. The adversary is checking if Y1 is equal to G of Y2, and that will always be true if the bit B was 0. That is how y was computed. So it will always be 1, trivial. And then we see what is the probability that adversary returns b dash equal to 0, provided actually this y was computed in the second method. So that is uniformly random string from capital L plus L bit length binary string. So what is the probability of that thing? So there are totally capital L plus small l number of bits in the string. So that total number of possible string is 2 to the power capital L plus L. Among that, what is the probability that this thing occurs? Even if it was chosen as uniformly random element from the space, what is the probability that this condition satisfies? So as this deterministic algorithm TRG, and so for having y1 as g of y2 in uniformly random string, we just get all possible combination of the last small l bit strings, and for each combination of small l bit string of the last part, that is y2, the y1 is fixed, right? So in the numerator we just get 2 to the power small l, and so after cancelling this factor, we get 1 by 2 to the power capital N, right? So now distinguishing advantage of the adversary. So this is what we call distinguishing advantage, right? So provided b is 0, the adversary return b dash equal to 0, minus the fact that b is 1. Provided b is 1, the adversary returns b dash equal to 0. So we compute the actually you can get a mod around this expression, that is the absolute value of this. It should not be negligible. So clearly 1 minus 1 by 2 to the power L is not negligible function, right? We already saw the concept of negligible functions. It is not negligible. Hence, G1 is not a secure PRG control, right? I hope you understand this thing. If you have any question, you can ask. So this was just a first option that we were seeing. I will just take a look at what was the question. What was the second option? So first one is already cancelled. It is not secure, right? We have already seen. If you want to try the second option yourself, anyone wants to comment? The second one is we propose another instantiation of PRG G2S, which is concatenating the output of original PRG GS with GS again. So the intuition is that clearly the output of G2S will have 2/2 of its output bit string, which are exactly equal to each other. So will this be a secure PRG? What do you think? Anyone wants to comment? Okay. So we'll proceed to the solution. So of course it is not secure again. The setup of the game is again the same. There will be verifier, there will be an adversary. The verifier will be tossing a coin and choose a bit B, 0 or 1. And the seed will be uniformly random from the L bit binary string space. And if B is 0, then Y will be computed as the G2 definition, that is GS concatenated with GS. Otherwise, Y is just a random 2L length bit string. And it sends Y to adversary. What adversary does is that okay, I think I can resume again. So we were seeing this second option of proposed instantiation of G2. So here as I said, the verifier and adversary are already there. So what adversary does upon seeing the y is that it parses y in y1, y2, so that length of y1 and length of y2 is equal to L. So basically it breaks the verifier's output y into two equal half, and then it checks if y1 is equal to y2. If it is equal, then it concludes that the y is actually generated by the first method, that is concatenating GS with GS. And if y1 is not equal to y2, then it returns b dash equal to 1. So now similarly, just as the previous example, we again compute what is the probability that adversary returns b dash equal to 0 when actually the selected bit was 0. So that probability is necessarily 1. Why? Because whenever y is computed in this method, GS concatenated with GS, so it will always be the case that y1 is equal to y2, right? So the probability is 1. And now if we calculate the probability that adversary returns b dash equal to 0 when actually the selected bit b was 1 and the string y was just a uniformly randomly generated string of the 2L bit length binary space, then what is the probability that y1 becomes equal to y2? That is, given a binary string of length 2L, what is the probability that first half of that string is exactly equal to the second half of that string? And it is just like, see, the denominator is just the all possible combination of binary string of length 2L, which is 2 to the power 2L. And in numerator, we fix just any one half of the string, and the second half is exactly same as that. So like that, the count is just 2 to the power L. We cancel out 2 to the power L from both numerator and denominator, and we get back 1 by 2 to the power L. Now, when we calculate the distinguishing advantage of the adversary, so that is the probability that A returns b dash equal to 0 when b equal to 0 minus probability that A returns b dash equal to 0 when b equal to 0. We take the mod value of this difference and we get 1 minus 1 by 2 to the power L, which is of course not a negligible function. And that's how we conclude that this second option, G2, this instantiation is also not a secure instantiation. Now let's see the third option. What was the third option? It was GS XORed with GS. So previous is GS concatenated with GS. The third instantiation that they're trying to propose is GS XORed with GS. So clearly, if you XOR GS with GS, you will get all 0 as the output string always, right? So it is very clear that whenever verifier gets b equal to 0, it computes y as GS XORed with GS, which is essentially going to be all 0 string in the output. And if b is 1, then it just chooses a uniformly random bit from the L bit length binary space. So of course, adversary will check if y is equal to all 0 of length L. If it is, then it will return b dash equal to 0. Otherwise, it returns b dash equal to 1. So here, what is the probability that A returns b dash equal to 0 provided b was actually 0? That is of course 1, because if GS is XORed with GS, it is always going to be output y as all 0, right? And the second case, that actually b was 1 and y was uniform random string from L bit length binary space, then the probability that adversary thought that it was generated from the instantiation G3, that is the case when that choosing all 0 of L length binary string among all possible combination of binary string. So all possible combination of L bit length binary string is 2 to the power L, and among them only 0 to the power L scenario will be chosen. That probability is 1 by 2 to the power L. Considering the distinguishing advantage, we get the mod value 1 minus 1 by 2 to the power L. Again, this is not negligible. So very similarly, as the previous problems, we conclude that G3 is not a secure PRG. Okay. Now, the last option, it was G4 is another instantiation. How do we output its? We output 1 concatenated with GS, where GS is secure PRG. Let's see the solution. Anyone wants to comment in the meantime? Okay. So this is also again very similar. So how the adversary try to distinguish? This is again will not be secure. How? So if b equal to 0, the verifier outputs y as 1 concatenated with GS, and otherwise it outputs uniform random string from 1 plus L length binary string. And adversary just checks the first bit of y. If it is 1, then it returns b dash equal to 0, else return b dash equal to 1. Then we can say that if y was actually generated by the first method, then of course always its first bit is going to be 1. So that probability that adversary returns b dash equal to 0 provided b equal to 0 is always 1. And then the probability when actually b was 1, so y was generated from uniform random choice of the output space, but still its first bit is 1, it is just half, because the first bit in general can be either 0 or 1. So the probability that first bit is 0, first bit is 1 is just half. Right? So distinguishing advantage is 1 minus half, which is half. This is a constant and not a negligible function. And hence, this last option, last instantiation of PRG, which is proposed in this question, G4 is not secure. Okay, so this question is done and all the options provided are not secure. Any question? Okay. So this is again a multiple choice question and you can answer it without pen and paper, just general concept. Anyone would like to answer? Which of the following is true about PRG? PRG is a deterministic algorithm. PRG is a randomized algorithm. We can construct a PRG which is secure against a computationally unbounded adversary, or a computationally unbounded adversary can always determine the seed of a secure PRG by seeing the output of the PRG. Which among them are true? Anyone wants to answer?
The first one is true. The
Yes.
fourth one is also true.
Okay. Yes, you are correct. So PRG algorithm, as we know, is always deterministic algorithm. And PRG is secure just because we have the adversary as computationally bounded adversary. Otherwise, if it is allowed to check, exhaustively search for all the possible seed from the input space, then it can essentially find out what is the seed by seeing the output of the PRG. Because the algorithm of PRG is already known, so it just checks by exhaustively giving the input seed from the all possible input space and check if it outputs the same string. So if we are allowed to have unbounded adversary, we can never construct a secure PRG. Just because we have bounded adversary, we are able to design a secure PRG. Right. Thank you. So we proceed to the next question. Again, we are provided with some proposed instantiation of the PRGs. Here the input space is m-bit binary string and output of the PRG is n-bit binary string. Of course, n will be greater than m. Now there are some proposed instantiation of PRG. G dash is first one is C dash is taking a seed S1 concatenated with S2. So two seed of the original PRG are concatenated as seed for G dash, and G of S1 XORed with G of S2 is a secure PRG. That is a claim. We don't know if it is true or false. And another instantiation is given as G dash with input C dash S1 concatenated with S2. That is outputs S1 concatenated with G of S2. Okay. So the other two option is just negation of that this is not a secure PRG and this is not a secure PRG. So any two of them will be correct.
In the second
Yes.
option, I think the output size will change from n to something m plus n. Is it so?
Uh, so S1 is of length m,
M.
yeah, and G of S2 is n. Okay. So yes, this is correct. So this thing should be n plus n. So you have correctly pointed out the thing. Thank you. Yeah.
Yes.
Output space will be m plus n, right? Any comment about whether it will be secure?
Yes, I think like the first two are secure.
What is the intuition behind that?
Yeah, that is because if you even if you take like two seeds concatenated, it is still a kind of like random seed of 2m length. So and the output that you are getting here as like g of s1 getting XORed with g of s2. So that output is still a random output, kind of random output, which can be an output of a PRG.
Okay. Okay, let's
So
okay. So as you have correctly pointed out that this is indeed a secure PRG. So how do we prove actually formally? So let's see the formal proof. So if we want to say some system is secure, we can take an approach that we will show that if this is not secure, so if there exists some distinguisher D which is effectively able to distinguish the output G of S1 concatenated with G of S2 from some uniform random string of the output space, then then we can use that distinguisher to distinguish between the output of original PRG, which is believed to be secure, from uniform random string of the output PRG space, original PRG's output space. Okay. So we will show here that formal proof. So let's design the game as with a verifier, with an adversary, and with a distinguisher. So the adversary will use the distinguisher to effectively distinguish between the output of original PRG and uniform random binary string of its output space. So here again verifier will toss a coin, choose some random bit p 0 or 1, and it will also sample s1 s2 as uniform random seed from the input space which are of length m. If b is 0, then y will be g of s1 concatenated with g of s2. Otherwise, it will just be some uniform random string of 2n length binary space. Now it will provide this y to adversary. And what adversary may do with this y is that it can parse y into y1, y2 such that y1, length of y1 and length of y2 are both n. Okay. So it can compute then y dash is equal to y1 XORed with Y2. So basically it gets a 2n length string. It divides it into two halves of each of length n, and then it XORs with each other. Okay. Now, then it provides this Y dash to the distinguisher. So why is that? Because we define G dash as G of S1 XORed with G of S2, right? So now that we assume that this distinguisher is actually able to distinguish any form of string which is generated from G of S1 XORed with G of S2 from any uniform random string of length n. So believing that such a distinguisher exists, so this distinguisher will of course output B double dash, again some bit, and the adversary will return B dash equal to B double dash only. Whatever it gets from the distinguisher as result, it will just send it back to the verifier, and this adversary will actually be able to successfully distinguish between G and output of G and uniform random string of length 2n using this distinguisher. Why? Because view of distinguisher D is exactly same as G of S1 XORed with G of S2. Why? Because whenever B is 0, so Y is of the form G of S1 concatenated with G of S2. Each of G of S1 and G of S2 are of length n, and adversary just XORed the first half with the second half of the string Y and computes Y dash. So Y dash becomes of the form G of S1 XORed with G of S2, and that is what the distinguisher D expects to distinguish from a uniform random string. So the view of distinguisher is exactly same as if Y dash is computed using this method, G of S1 XORed with G of S2. And if B is 1, if this is Y is uniform random string of length 2n, then XORing its first half with the second half is again a uniform random string of length n. So that is what distinguisher D expects. And in that case, distinguisher is actually, if we assume that distinguisher is successfully able to distinguish between these two cases, then it correctly outputs B dash, and then adversary will also correctly output B dash. And then the adversary is actually able to distinguish between these two cases, output of PRG and uniform random string of length 2n, but which is of course not a case, because one thing I should mention here, that original PRG that was given in the question is from the space input space M to output space N, and we are actually using the assumption that given this is a secure PRG, another PRG G1 which just concatenates the input seed S1 concatenated with S2 and output C of S1 XORed with G of S2 is a secure PRG. How this is secure? It is already provided in the lecture, NPTEL lecture, which are uploaded in this website. So you can check there. This thing is already proved there by hybrid arguments. So you can check it there. And from there, assuming this is true, I am proving this statement that G dash is a secure PRG. Okay. Right. So, and because we know that this G1 is secure, we can say that such a distinguisher cannot exist, right? So that's how we prove that an instantiation of PRG G dash is actually secure with this method, right? So, and now proceeding to the next instantiation, which is G dash of S1 concatenated with S2 gives S1 concatenated with G of S2. This is secure or not. So as we will see that this is again also a secure PRG. And how is it so? So G is provided as already known to be secure PRG. Now again we have verifier, adversary, and distinguisher in the scenario, and verifier randomly chooses a bit 0 or 1, and a seed S2, which is from the input seed space, which is M length binary string. And then if B is 0, then Y is G of S2. Otherwise, Y is uniform random string of length N. And it provides the adversary with this Y. What adversary does is that it just samples some S1 from the space M length binary string, and it concatenates S1 with Y. So that this form is nothing but of the form S1 concatenated with G of S2. So such formulated Y dash is then provided to the distinguisher to be distinguished whether it was from of the form S1 concatenated with G of S2 or of the form uniform random string from the output space. So again, we argue in the same way that the view of distinguisher is same as seeing S1 concatenated with G of S2 whenever B is 0. And whenever B is 1, that is Y is uniformly random string, and then concatenating Y with some M length uniformly random string will give another uniformly random string of length M plus N. Right. So using the distinguisher, then the adversary will successfully be able to distinguish between the output of original PRG and a uniform random string of length N. But which is not true, because G, original PRG, is already believed to be a secure PRG. So that's how we say that such a distinguisher cannot exist, and we argue that this given PRG is indeed a secure PRG. Any question? So original question was this, and our conclusion is the first two statements are correct statement. Which of the following are false? So last two were false. Any question about till now? Okay. So we are almost to the end of the session. So just two of the questions are left. So next problem here, again we are talking about some secure PRG, which is G from input space of length N. The seed is of length N and the output is of length L1N. And now again we are being asked to explain if the following constructions of PRG are secure or not. The first construction G1S is G of S XORed with 1 to the power L1N. So L1N is some function of N. Of course, L1N has to be greater than N because G is a PRG and expansion is property of PRG. So 1 to the power L1N means just string of all ones of length L1N. And the second instantiation of PRG is G of S concatenated with 1 to the power L1N. Now, these two constructions are secure or not. So, as we saw the previous two examples, in the first one, we proved some of the instantiation of PRG to be not secure by showing that the adversary can use some property of the output string to effectively distinguish that output of that instantiation of PRG from the uniform random string, and hence we concluded that they are not pseudo-random, so they are not secure PRG. And in the second example, we proved some instantiation of PRG to be actually secure by showing that if they were not secure and such distinguisher exists, then using that distinguisher, the original PRG can be shown to be not secure, which is a contradiction. So we have already seen how to show some instantiation of PRG is secure, or how to show formally some instantiation of PRG is not secure. So if anyone wants to try this thing, this question. So we will proceed. The first question, the instantiation of PRG is just XORing the output of original PRG with all ones of length L1 in. So what happens is that we show that this is a indeed secure PRG. Again, there comes verifier, adversary, and distinguisher in the scenario. And if the verifier chooses bit B as 0, then it outputs Y as G of S. Else it outputs a uniform random string from L1 in length binary string. And it provides Y to the adversary. What adversary does is that it computes some Y dash by XORing Y with all one of length L1 in. So basically XORing all one to some binary string just flips each bit of that original binary string. So Y dash is nothing but one's complement of Y, right? So obviously distinguisher gets Y dash, and what it sees, so view of the distinguisher is exactly same as GS joined with 1 to the power L1 n if the chosen bit B was 0. And if the chosen bit B was 1, that is Y was uniformly random string, then uniform random string, just one's complement of uniform random string is also uniformly random. So in that case also, view of the distinguisher is just as it is viewing a uniform random string of L1 in length. So as we assume that there is some distinguisher who is effectively distinguish how Y dash was generated, so it will output some B double dash, and adversary will output exactly that bit only. So B dash equal to B double dash, it will output the verifier. And as distinguisher is effectively able to distinguish between these two cases, this adversary also should be able to effectively distinguish output of the original PRG G from the uniformly random string of length L1 in. But as we know that this given G is already a secure PRG, pseudorandom is already satisfied by it. So such a distinguisher cannot exist. Analogously to just as the previous examples, so such a distinguisher cannot exist, and we conclude that the given instantiation of the PRG is a secure PRG. And coming to the next example, here we are just concatenating L1 n number of ones to the output of original PRG. Anyone wants to comment on that? What this case will it be secured or not? Is the adversary somehow able to distinguish such kind of string from uniform random string? Okay, let's just wrap up within 10 minutes. Okay, so here also the PRG is not secure, because it is very trivial to see that as the instantiation of this PRG G1 always concatenates all ones to the output of GS. So the very naive method that adversary can take to distinguish the output of G1 is from uniformly random string of length L to L1n is that it will check if the output Y, the last L1 in number of bits of Y are all ones or not. If it is all ones at the last L1 in number of bits, then it will return B dash equal to 0. So it will say that Y was generated using the first method, GS concatenated with all ones. Otherwise, it returns B dash 1. And then what is the probability that adversary outputs B dash equal to 0, provided B was actually 0? That is 1. Of course, if it is that is how y is generated, then of course last L1 number of bits will always be 1. And if it was generated uniformly randomly sampled from L1 in length binary string space, and then what is the probability that all the last L1 bits are ones? That is, so the denominator has 2 to the power 2 L1 in, that is the length of the output. And as the last L1 n number of bits are to be fixed as 1, so we get as the numerator 2 to the power L1, and by cancelling out we get 1 by 2 to the power L1n. So the distinguishing advantage of the adversary is 1 minus 1 by 2 to the power L1n, right? So you actually take mod of these two probability. So anyway, so as we are the adversary is effectively able to distinguish these two cases, so this is not a secure PRC, right? So this is the last question that we have on this slide for today. So let G be a pseudo-random generator with expansion factor L of n greater than 2n. What do we mean by that? The seed is of length n and the output of PRG is of length ln such that ln is greater than 2n. So in the following case, say whether G dash is necessarily a pseudo-random generator. So how G dash is described is that G dash S is equal to G of S concatenated with G of S plus 1. So notice that there are relation between the seeds that are being used in using the pseudo-random generator G twice. So G dash uses the secure PRG G twice, but the seed it provides to G are actually related to each other. So I will just discuss the solution here. So this is not going to be secure PRG. For proving that, so we assume some secure PRG H which maps n-bit seed to 2n-bit output. So H is a secure PRG. And then we define G of S as H of S1 to Sn minus 1. So although H is defined on n-bit input seed, if we define another instantiation of PRG which is just using first n minus 1 bit of the seed, then if G is secure, if H is secure, G is also secure. Why is that? Because G on input a n-bit seed, S is of length n, so G on input a n-bit seed behaves exactly in the same way as if H were provided with a n minus 1 bit input, and H is already known to be secure PRG. So like that, we are just defining a PRG G, okay, with the help of another secure PRG H, and we say that if H is secure, G is also secure. Now, using such an instantiation of secure PRG G, we say now that G dash S, if we define as GS concatenated with GS plus 1, what we get is that H of S1 to Sn minus 1. So each of Si is the ith bit of the seed string S, right? So GS we have defined as this. So it just uses first n minus 1 bit of the input string. So H of S1 to Sn minus 1 concatenated to H of S1 to Sn minus 1 again. Why? Because S and S plus 1 will just differ by the last bit, right? So if S has last bit, nth bit as 0, then S plus 1 will have last bit as 1. But as G of S is defined so that it uses only first n minus 1 bit, so the last bit difference does not matter. So first half of G dash S will be exactly equal to second half of G dash is, right? So that's how. Now we have already seen previously that if some PRG's output is such that first half of the string is exactly same as second half of the string, an adversary can essentially distinguish that from a uniformly random string with non-negligible probability, right? So by that observation of our previous problems, we can say that G dash S is also not necessarily secure. Of course, it depends on the instantiation of GS, how we instantiate GS. But our question was whether G dash is necessarily a pseudorandom generator or not, and we should always think of all possible cases. So if GS is defined in such a way that it just uses first in minus one bit of the input seed, then it will be the case that it does not matter what is the last bit of the seed, and the first half and the second half will exactly be the same. The main issue of this construction is that G dash uses a secure PRG G twice with input seed which are correlated to each other. So that should not be the case of any construction of PRG. So we conclude that as these two seeds were related to each other, that's why this is not secure. Okay. So any question of any of the attendees? Okay. So if you don't have any questions, so I will just end this meeting. Okay, there is some message. Can you please display problems 1 to 6 so that I can take? Actually, I think I will upload this PPT to a Google folder, and link of that Google folder will be shared with all the NPTEL course attendees. Okay, so that's not a concern. Although I can just over, but okay, I can. I think this meeting is already going to end. Hmm. Can you just please unmute and say which slides you 1 to 6? Hello, Dave, right? Just tell me where should I stop, which slide you are talking about. Problems 1 to 6. Here is problem 1. I think the meeting will be ended. Okay, so and don't worry, they will be shared with you, all the PPT thing, right? Okay, thank you for attending.